we will do the Stoats dataset first. So I'm going to click on Stoats. No, close. That's not very helpful. Okay, so this is hopefully, yes, good. 2 sets of data. I have 2 islands, which are very excitingly called Island J and Island K. I don't know what we could call them, Jura and I don't know, what's a Scottish island beginning with K? Anyway, there's 2 islands called Island J and Island K. And we believe that stoats, which are the small weaselly kind of things that you make ermine out of and make brushes out of if you do painting, we think that on the 2 different islands we've ended up with different species, and we think that the characteristics of the species is to do with tail length. So what we've done is measured the tail length of the stoats on Island J, and we've measured the tail lengths of the stoats on Island K. So our hypothesis is about, are the mean tail lengths the same on Island J as Island K? Our first thing, just to have a little show of you, we're going to do the usual exploration. So we've got tail length. The island is going to be a factor because we're going to split into 2 groups. Actually, I'm not going to do any plots at all, so let's not worry about that. We're just going to calculate statistics and go OK. So I summarise the data, and so the mean length of tails on Island J is 107. The mean length of tails on Island K is 100. So there's looking like there might be a bit of a difference between those 2. These are distance lengths in millimeters. Potentially there's a difference. Now, having another little bit of a look, you can see here that the lowest band of the confidence interval for K is 98.53. The upper bound of the confidence interval is 102.37. And the confidence intervals for the J island are 102.71 and 117.09. So those 2 things don't overlap with each other. This is suggesting to us that there might actually be a difference in tail lengths between the 2. But we have to do a hypothesis test to prove it. Now, with all hypothesis tests, the null hypothesis is that there's nothing happening. So the null hypothesis in this case is that there's no difference in the mean length of tails between Island J and Island K. So that's effectively saying that the animals on both islands come from the same population with the same average tail length. Now we want to do the hypothesis test to see if that's true. So if we go to Analyze, and we're comparing the means of 2 groups. So we're doing compare means. Now here in this menu we have quite a lot of choices as to what we want to do. Oh, interesting, they've introduced the Z test as well. Let's not pay any attention to the Z test and just stick with t-tests. You've got means, which is the top choice that you can do to compare the 2 means. I'm not exactly sure what that does, but it's not what we want to do. Next is the 1 sample t-test. Have we got 1 sample from 1 island? No, we've got 2 samples, so we don't want to do that either. Are the samples on Island J and Island K independent of each other? Yes. Have we summarized them to get means and standard deviations that we want to do the comparison to? No, we've got the actual data. So that means yes so far to independent samples t-test, no to summary independent sample t-test. Is it a paired sample? Have I made multiple measurements of the same things? No, I haven't. The animals on Island J are different to the animals on Island K. if I took the animals from island J and put them on island K and then saw if they changed their size, then I'd be measuring the same animals twice, but that's a bit silly. And have I got more than 2 groups? No, I've just got 2. I've got island J and island K, so I don't want to do ANOVA. So this is an example of an independent sample t-test. So I want to click on that. So it asks me, what is the hypothesis about? The hypothesis is about the length of the tails of the stoats. So that's the test variable. Now, what variable groups the data into 2 different groups? Well, whether they're on island J or island K. So that's a grouping variable. And now I have to define what the 2 groups are. Now, you could, if I'd got these numerically as 1 and 2, then I could just use 1 and 2. Otherwise, I can use J. Oh, good. I'm going to use 1 and 2. Let's cancel for a second. For the simple reason, if I'd have done view, if I go back to the data. So here it says J and K. If I go view and get rid of the value labels, they are actually 1 and 2. The labels on them are J and K. It is usually a better idea to do that, to have your data so that you number the groups and then add labels to them, rather than using their labels as the group definition. So independent samples t-test, let's just set that up again. And then island is the grouping variables. I've got group 1 and group 2. Now I could switch this round and have group 2 against group 1. So one of the islands has tails longer than the other. So if I put that as group 1 and then I do the difference to group 2, then the other group is smaller, so all the differences will be negative. Whereas if I have the smallest group first and the biggest group second, then all the differences will be positive. I'm going to leave it as 1 and 2. But that's just to say, whichever way around you put your data into the program depends on whether you get a negative value for the difference or a positive one. It doesn't matter. The only thing that matters is the size of the difference, not whether it's positive or negative. Continue and press OK. And that's it. I've done my hypothesis test. So the first thing, as usual, SPSS tells you what it's done. It tells you that there are 15 measurements on island J. It tells you that there are 20 measurements on island K, that the mean size on mean length on island J is 107.4, standard deviation is 8.475, standard error of the mean is 2.188. For island K, it's 100.45, standard deviation 4.097, standard error of the mean 0.916. The next thing it does is gives you this table, which is the independent samples test, independent samples t-test. Now, SPSS does it assuming 2 different things. First is you do a Levene's test to check if the variances are equal. In this case, it's done the Levene's test. It's got a test statistic of 9 point whatever it is. It's got a significance value of 0.004. Now, the null hypothesis, as usual, is that nothing's happening. So the null hypothesis is the variances are equal. And this is telling you quite clearly the variances are not equal. So you don't want to use this row of the table. You want to assume this row of the table, which says equal variances not assumed. Now I'm going to tell you something special. Never ever in your entire life and for any reason use that top row. Just don't. The t-test was invented in 1920. It has some biases and weaknesses, particularly that the size of the sample on island J is not the same as the size of the sample on island K. As well as that, there's quite a big difference in their standard deviation and their variances. So in the 1930s, they developed a new version of the t-test, which could take into account having different size samples and different variances. This is a more general version of the t-test. Does exactly the same hypothesis question. It just has more complicated maths to avoid there being any kind of bias. So that means that the old original version of the t-test, which is what corresponds to that original top line, is no longer valid and has not been valid for the last 80 years. No one should ever be using it, and you should only ever use Welch's new version of the t-test. Under Welch's version, you see that the t-test statistic itself is slightly smaller, but the biggest change is to do with this thing called degrees of freedom. Under the standard t-test, what you did is add up how many there are in the two different groups and then subtract 1 from each one of the groups. So in total, there are 35 minus 2, 33. Under the new one, there's a horrendous formula. Don't need to worry about it. SPSS has done it for you. Under this one, under the original formula, it could only be an integer. Now it can be non-integer, which is fine. Then you have the p-values for the tests. Now this is a good thing because SPSS has finally gone around to updating it so that you can have one-sided and two-sided values. I said the null hypothesis is that there is no difference between the length of the tails on the two islands. So that means if there's an increase in the tail size or a decrease in tail size, either of those alternative hypotheses are valid. So that means I've done a two-sided test. So my p-value is 0.009. If I did something which had a single-sided hypothesis, then I would use this other p-value. Now, single-sided hypothesis is, let's say I want to see if men are taller than women. So I'm not saying that men and women have different heights. I'm saying that men are taller. So that means the hypothesis difference has a direction instead of it could be in either direction. So that's an example of what we call a one-sided hypothesis. The mean difference is 6.95, which is the same using both methods. Standard error of the difference is 2.372. And the confidence interval for the difference is between 1.983 and 11.917 millimeters. This suggests that island J and island K have two different types of stoat. So potentially you have got a different subspecies. Then it's got these other effect sizes. Occasionally you use Cohen's d. So in this case, it is Cohen's d's value is 1.097, and it's somewhere between 0.37 and 1.809. Cohen's d of 1 is a pretty big effect size. 0.37 would be a small effect size, and 1.89 would be a very big effect size. So you pick what you want to do. In general, I don't usually ask you for this. I only ask you for that. And when you're reporting in papers, you would say, I've done a hypothesis test. There is a significant difference in the length of the tails between the two islands. The p-value is less than 0.009, which is less than 0.05. And the confidence interval for the difference is from 1.983 millimeters to 11.917 millimeters. Bear in mind, I did them to the whole millimeter. It's going to be 2 millimeters to 12 millimeters. Is the confidence interval for the difference. That's it. That's the complete analysis done for that particular set of data.